All right, so we're going to look at section 4.2. As I said before, we're going to split it into 2 days. So we're going to look at graphing. And really, the two cases we look at are graphing when the numerator is bigger, has a bigger degree, and then when the denominator has a bigger degree. Okay, so we look at both of those. And we'll also look at the case when they're equal. Okay, we'll do that as well. Okay, so just a reminder, something I've mentioned a couple times, okay, and John mentioned it earlier. Okay, if you have a rational function and you have a common factor in the top and in the bottom, you don't have an asymptote. Okay? What you end up with is a hole in the graph. Okay, and the problem with that is if you're graphing and you're just trusting the calculator wouldn't show you the hole. Okay, so I'll graph something like an example 1 so you can see what that looks like again. Right, so I'm just going to type in x minus 1 divided by x minus 1. And does anybody know what that's going to look like? You're dividing two things that are the same. So what happens when you divide two things that are the same? What do you get?
0. You get 1.
You get 1. So basically, this is going to look like a line y equals 1. But it's not a line. There's going to be a hole in it. Okay, where is the hole going to be? Yeah, Ian?
1 sounds about right.
Yeah, it's going to be a hole at 1. Okay, because that's the value that would make the denominator 0. Okay, so I hit graph. Let me just do a standard window. Okay, and there's my line. It looks just like it looks like a line, but there's a hole at 1. Okay, I can verify that by just going to table. I type in 1, I get an error. Now you can type in anything else as close to 1 as you want. You can type in 1.001, and that works. You can type 0.999, okay, as close as you want, and that works. So the hole it's infinitely small. Okay, it's just at 1. Okay, anything to the left or anything to the right, no problem. Okay, how about graph like that? Would that graph have a hole in it? What do you think? How about Nick? What do you think? Is that graph going to have a hole in it?
Yes.
All right. What's the common factor then in the top and in the bottom?
1.
So the factor, it has a letter in it too.
X.
And a number.
Minus 1.
X minus 1. Okay, so the common factor in the bottom is x minus 1. In the top, it's x minus 1. It's just there's 2 copies of x minus 1 in the top, 1 copy in the bottom. So if you were to divide them, basically what's going to happen? 1 copy of x minus 1 is going to disappear from the bottom, and 1 copy from the top. So you're going to be left with basically something that looks like y equals x minus 1. It's going to be a line with a slope of 1 and a y-intercept at 1. A negative 1, thank you. But it's not really a line. Okay, there's a hole, but you can't see it on the graph. And the hole, again, is at 1. Okay, it doesn't give me a y value. Any questions on that?
Kind of scary. How was it?
Yeah, I know it is. It's scary. You can't see it.
You don't notice it.
Yep. All right, so keep in mind, at those 2 points, what we had there, that was called a discontinuity. Meaning, if you really wanted to sketch this on paper, okay, you'd have to draw it, pick up your pencil, okay, make sure you leave a hole there, and keep drawing it.
That's a pretty good lines here.
Thanks.
You practice?
I do. Every day.
That's a talent, like draw lines all day. Perfect as possible.
Okay, and this kind of gap in the line, it's what we call a removable discontinuity. Okay, because it's so small, we could almost remove it and just fill in a single dot, and then we'd have a continuous line. Okay? If you have something like this, let me make it so the top and the bottom do not have a common factor. Okay, that graph is not a removable discontinuity, okay? Because the problem is we have a vertical asymptote. It's not like if we just filled in one tiny little dot, we'd have a continuous line, okay? This asymptote, we have much more of a problem, okay? It's curving up to infinity, down to negative infinity. So asymptotes are not removable discontinuities, but a hole is because it's so small you can barely see it. Right, so any questions on that? Difference between what a removable discontinuity is versus something like an asymptote. The asymptote's a much bigger problem than just a small hole. Okay. All right, so suppose that we have some type of rational function. Okay, could be just like this. Right? What I wrote here is the same thing I wrote here. This is just kind of generic. So you've got some highest term, plus or minus, then the next lowest exponent, all the way down to the constant. And the same thing in the bottom, another polynomial in the bottom. What term in the top is going to control everything that happens? There's one term in the top that tells you what, if you zoom out enough, what kind of the big picture idea. Yep. Right, the first term. Right, the first term is what we call the end behavior model for the numerator. And remember, there's 4 different end behavior models. You've got up, up, you've got down, down, and then you've got one up, one down, either way. Okay, so there's four different end behaviors. And does anybody remember how you can tell looking at that first term? There's two things you have to look at. How about the exponents? Anybody remember what you look at for that?
Even or odd.
Yep, you look at whether it's an even or an odd. If it's an even, that's like a parabola shape, either up, up, or down and down. Okay. What else do you look at? Besides the exponent being even or odd, the coefficient, and you got to see whether it's positive or negative. If it's positive, that with an even exponent, that would be up and up on each end. Okay, and we can do the same thing in the bottom. Okay, the first or the highest degree term, usually the first term, if you write it in descending order. That's your EBM for the denominator. But now my goal is to find an EBM not for the top separate and the bottom separate, but for the whole thing. Okay, for this whole function. So if you know the EBM for the top and you know the EBM for the bottom, what do you think you would do with both of them to find the EBM for the whole thing?
Combine them.
How would you combine them?
Divide.
By dividing them. Yeah, you just divide them.
What is EBM?
End behavior model. All right, so if you want to know the end behavior model for the entire function, take the EBM in the top, take the EBM in the bottom, and then just divide them. Okay, now does anyone remember the rule when you divide two things with the same base? What do you do with your exponents? You subtract them. So basically what happens is you're going to have a sub n, which is going to be whatever that number is in front of the term in the top, b sub m. Okay, that's whatever the number, bless you, whatever the number is in front of the term in the bottom. And then the x is going to be whatever that comes out to, x to the n minus m. Which is what I just wrote below. And that's the end behavior model for the entire function. Just divide the one in the top by the one in the bottom. Okay, and remember that the EBM is handy because it tells us basically if you zoom out enough, what the function basically looks like. Okay, the other terms, they're not really that important. They're going to cause maybe little twists and turns in the middle, but big picture, all you got to do is look at the first two. Now, something can happen, especially when m is bigger than n. What can happen in that case if m is a bigger number than n?
This could be negative exponent.
Right, you could get a negative exponent, okay, something like this. Does anybody remember what you do with negative exponents to make them positive? Think of that as a fraction. Yeah, you put it to the bottom. Okay, if you have a negative exponent and you want to make it positive, we just put it in the bottom. Okay, so if I had something like x to the negative 2, what would that be as a positive exponent?
1 over x squared.
Yeah, 1 over x squared. Okay, so anytime negative exponents come up, that's what I'd like you to do. Just make it positive. Okay, so any questions on that? All right, so let's find our end behavior model, and then we'll use it to get the horizontal asymptotes. And I'll show you how you use it. Okay, Hannah, what's the highest degree term in the top?
2.
Can you tell me the whole? So that's the highest degree. Can you give me the whole term? But you were correct.
To the second.
Yeah, 2x to the second. And can you give me the whole term that has the highest degree in the bottom?
3x.
3x to the third. Okay, now when I divide these, all my x's are going to cancel out from somewhere. Am I going to be left with x's in the top or in the bottom? I'm going to be left with some in the bottom because the exponent, 2 minus 3, that's a negative 1. Or if you don't like to think about negative exponents, think about it this way. Okay, you've got 2 x's in the top, so you can cancel 1, 2 in the top with 1, 2 in the bottom. So what am I left with for my final answer? 2 over 3x. That's the end behavior model. So in other words, if you were to graph the original problem and you graph what we just wrote and you zoom out enough, they would basically look identical. All right, now to find the horizontal asymptote. Okay, the first time I'll write how to do it, and then after that, just have to remember how to do it. Okay, so take the end behavior model and let x approach infinity. And basically tell me what happens to the EBM. So let x approach infinity, or let x approach negative infinity. You're going to get the same result. And see what happens to EBM. Okay, so now the first step in finding a horizontal asymptote is find the EBM, and then take what you just found and let x get really big. Okay, let it get bigger and bigger and bigger in this fraction, and tell me what happens to that fraction. Okay, so what's going to happen to the fraction as x gets bigger and bigger?
Fraction gets smaller and smaller.
It's going to get smaller and smaller, and what does the fraction approach?
0.
It approaches 0. Okay, pretend like x is 1,000. Right? You'd have 2 divided by 3,000. Okay, pretty small. Then let x be 1,000,000. Okay, 2 divided by 3 times 1,000,000, that's 2 divided by 3,000,000, even smaller. So it's going to get smaller and smaller and approach 0. Will it ever reach it?
No.
No, because no matter if you take 2 and divide by 1,000,000,000, it's small, but it's still not 0. But it will approach 0. So that is your horizontal asymptote. It works exactly the same way if you let x be negative infinity. Okay, pretend like x was negative 1,000,000. Bless you. That's 2 divided by negative 3,000,000. Still very, very, very small, approaching 0. Let's try this one. What's a little different about this problem compared to the one above it?
That one's bigger.
Which one?
That one's bigger.
It's bigger? Oh, you mean like more terms?
Yeah.
All right, what if you just focus on the leading terms? Look at the exponents. They're the same. Okay, so something a little different is going to happen this time when we divide them. Denver?
It's just going to be 2. It's just going to be 2.
Yeah, the end behavior model is just going to end up being 2 over 3. That's the biggest term in the top. That's the biggest degree term in the bottom. And whenever your exponents are the same and you divide them, they cancel out. And you're just left with 2/3. So this time, the end behavior model is just a number. There is no letter. Okay, but I'm still going to ask you the same question and see if you can tell me what's happening. Okay, as you let x get bigger and bigger in that fraction, 2/3, what does that fraction approach?
Remains at 2/3.
It just stays at 2/3. There is no x in the fraction. So as x gets bigger and bigger, y always stays at 2/3. And that's your horizontal asymptote. So in the case where the exponents match in the top and the bottom, the EBM and the horizontal asymptote are the same. In the case when the degree in the top is smaller, then they're not the same. Okay? Asymptotes always have to equal numbers. There's never any letters in an asymptote. But an end behavior model can have a letter. Okay, it depends. Right, so any questions on the end behavior model or horizontal asymptote of that one? All right. So we're going to focus on the kind of problems that we just looked at. Okay, when the degree of the numerator is either smaller or equal to the degree of the denominator. Okay, and that's all we're going to look at today. In example 2a, the degree of the numerator was smaller. In example 2b, they were equal. In both cases, notice you got a horizontal asymptote. One of them was at 0. One of them is at a constant, a little bit above 0. Okay, at like 0.6 repeating. Okay, so what I'm going to give you is some hints on how we can sketch these graphs, because they can look pretty complicated, but if you understand how to find asymptotes and use your graphing calculator, it's not too bad to sketch it. All right, one thing that's can be helpful when you're sketching a graph is to try to find your intercepts. Where does the graph cross the axes? Okay, to find your x-intercept, that's when you plug 0 in for y. And when you find your y-intercept, that's when you plug 0 in for x. Now, the reason I say this can be helpful is because it doesn't always work. You could have a graph that never crosses the x or the y-axis. Okay, as an example, just okay, that graph will cross both the x and the y-axis. Okay, crosses the x-axis here and the y-axis there. But if I graph this one, this graph doesn't cross either axis because both axes are asymptotes. All right, so in this case, step 1 wouldn't help us too much, but we'll always try to do step 1 and see if it helps. Okay, step 2. Okay, find your vertical asymptotes. And when we sketch an asymptote, how do we sketch it? How do you show me that it's an asymptote?
Dotted line.
Yep, put a dotted line. Okay, and I've got to add something to what I put in parentheses. The vertical asymptotes are the zeros of the denominator as long as you don't have what? Because if you have what I'm thinking, you would have a whole, a common factor. Okay, so the vertical asymptotes are the zeros of the denominator as long as you don't have common factors. Okay, so always check that and make sure that you actually have an asymptote and not a hole in the graph. Okay, next thing we're going to do when we make a sketch, we're going to find the end behavior model, and that's going to directly help us to get the horizontal asymptote. Okay, so you're going to see a lot of abbreviations. I'm going to use VA for vertical asymptote, HA for horizontal asymptote, and EBM for end behavior model. Okay, so after we have our vertical asymptotes, then what I'm going to do is something I've shown you guys before. I'm going to check a point very close to it. So like, let's say I had an asymptote at 2. Okay, I'm going to check an x value at like 2.01, and I'm going to check another one at 1.99. And what's usually going to happen with a vertical asymptote, on one side you're going to be up very, very high. On the other side, it's going to be down very low. Okay, and the last thing we can always do is after we sketch it, use the graphing calculator to double check our sketch. Okay, even as I'm sketching it, I'm going to use the graphing calculator quite a bit. I'm going to use the table, just because the table can do arithmetic a lot faster than me trying to do it out by hand. Okay.
Could you go up like?
All right, so that's the first one we're gonna sketch a graph of. Okay, so there might be something I want to do right away that it's going to help us to find the asymptotes. It's going to make the denominator a little easier to look at. Curtis, can you remind me what I might want to do to the denominator? Something we've done before?
Factor it.
Yeah, let's factor it just so I can find the zeros of the denominator a little easier. Austin, what will be my first term in each parenthesis when I factor? Yep, I'm going to get an x and an x. How about Connor? What about my signs?
Negative positive.
Yep, negative, positive. Okay, we're going to need one of each. And two numbers that multiply to give me 6 and subtract to give me negative 1.
-6 plus 5.
They have to multiply to give me 6, though.
Negative.
Yeah, we got to use some combination of a 3 and a 2. I would say make the 3 negative, 2 positive. Let's check it. It's 2x. Take away 3x. It's negative 1x. Yep, so that's good. All right. So now I'll go through all the steps and see what I can do. Okay, let's find the intercepts. Okay, I'll start with my x-intercept. To find my x-intercept, what letter do I let equal 0?
Y.
Let y equal 0. Remember, that's y. So if you set this fraction equal to 0, you'd have 0 equals that fraction. What's the only way that a fraction can equal 0? Brad? Nope, 1 divided by 0 is undefined. How do you do a division problem and get 0 is the answer?
0 over
Yeah, 0 over a number. The only way you can have a fraction equal to a 0, okay, pretend I just filled in 0 right there, is if the top is 0. So what would make the top 0? 1. That's my x-intercept. So this is going to cross the x-axis right there. Hey, it's a point on my graph. Maybe it'll help me when I make my sketch. Okay, my y-intercept. What do I let equal 0 this time? X. Okay, so if we let x equal 0, in the top, what's 0 minus 1?
Negative 1.
-1. 0 squared
0.
minus 0,
0.
minus 6.
Negative 6.
-6. Okay, so my y-intercept is 1/6. Okay, so it's going to cross the y-axis about right there. All right, so I've got those 2 points. Let's find the vertical asymptotes. So those are my zeros of the denominator, assuming I don't have any common factors. Okay, what's one number that would make the denominator 0? 3. And what's another number?
Negative 2.
-2. Okay, I'm going to sketch those right now. So vertical asymptote at 3 and -2. What else? Let's find the end behavior model, and that'll give me the horizontal asymptote. Okay, Ryan, what's the highest degree term in the top?
Which one?
For example 3.
X.
X, and the highest degree term in the bottom?
X squared.
X squared. So x over x squared. And what does that reduce to?
X.
1 over x.
1 over x. Thank you. Okay, so that's the end behavior model. Now, let x get really, really big and tell me what number that fraction approaches.
0, 0.
Yeah, it will approach 0. That's your horizontal asymptote. Okay, so draw that in. And now I'm going to use the graphing calculator to help me evaluate points near the vertical asymptotes. Okay, so again, I'm not using the calculator for the graph part. I'm just using it because it can do arithmetic faster than I can by plugging it in by hand. So I've got x minus 1 divided by x squared minus x minus 6. Okay, let's try a value very close to -2. What's a value just to the left of -2?
Negative 2.1.
Even closer.
2.01.
Yeah, -2.01. Okay, I'm way down at -60. Okay, so just to the left of -2, way down there. What's a value just to the right of -2?
Negative 1.99.
-1.99. And all of a sudden now we're way up at +60. Way up here. Let's do the same thing with 3. What's a number just less than 3?
2.3.
And just after 3?
3.2.
Perfect. So 2.99, 3.01. Okay, just before 3, you're way down. Just after 3, way up. Way down and way up. Okay, and we already know the horizontal asymptote is at 0. So as x gets really big, my y value is going to get closer and closer and closer to 0. Okay, heading to the right, it's going to be just barely a positive number. Okay, just barely positive. Heading to the left, it's still approaching 0, but this time it's a negative number. So just barely below 0. Okay, now we need to connect all these dots. Okay, I'm going to start in the lower left. Okay, you've got to connect those 2 dots. It has to be a curve getting closer and closer to the asymptote. Okay, so that one's very close, starts to get further away, but then it has to curve down and start getting closer and closer to that one. Okay, same thing's going to happen in the upper right. It's got to stay in that section. It can't cross those dotted lines. So it's going to come down, get further away, and start curving towards the other one. Okay, and in the middle, well, I've got to connect all 4 of these dots, and it has to be a curve. So it's going to almost look like a cubic function in the middle. Okay, this is going to come down. It's going to go through those dots, and then continue going down. So that's exactly, if I hit graph, it should look pretty close to that. Pretty close. Okay, theirs was a little bit flatter in here. That's fine. Okay, if you have what I put on the board, that's what I'm kind of going for. But, yeah.
Can you go through how you get the y-intercept again?
The y-intercept, that's just fill in 0 for x everywhere. So you get 0 minus 1 divided by 0 minus 0 minus 6. So it's negative 1 over negative 6.
And then what's that on the graph? That's what y-intercept, right? So
That was the y-intercept. Yeah, so 1/6 is, I tried to draw it right about there.
the x?
The x-intercept?
Yeah.
So the x-intercept is when you set this equal to 0. Okay? Pretend like this is y equals. Now you're plugging 0 in on the left. And the only way a fraction can equal 0 is if the top is 0. Doesn't matter what the bottom is. As long as the number that makes the top 0 doesn't also make the bottom 0, that's a problem. Okay? If that ever happens, then that means your graph doesn't cross the y-axis. Okay, any questions on that one? Yeah?
Why are you able to go through the horizontal asymptote for the middle line?
Because remember, asymptotes predict what happens as you get far away, as x gets huge. We're talking like millions, billions. So if you cross an asymptote near 0 or 1, that's fine. You just don't want to be crossing the asymptote when x is heading towards infinity. Okay? But that'll usually happen like that. Okay, any other questions on that? All right, so let's take a look. We have 2 more, pretty much the same. That's a degree where the top is smaller, and this is where they're the same. So we just did one, I think, where the top is smaller. So let's we'll finish up with one where they're the same. All right, so I'm going to start with my vertical asymptotes. Okay, Austin, bless you. What should I do to my denominator to make that a little easier to find my vertical asymptotes? Yeah, let's factor it. I'm going to keep the top. Let's see, does the top factor? And Austin, what can you factor out of each term in the bottom?
X.
Yeah, all you can factor out is an x. So this isn't the complicated type of factoring. You're just going to take out a single term, and then you'd be left with x minus 5. Right. So Luke, where's one of my vertical asymptotes?
Would be 2x minus. Yeah, that would be
Yeah,
2x.
Oh, yeah, thank you. That's going to change my answer. Can you tell me where one of my vertical asymptotes is?
2.5, right? Because 2
Yep.
has.
You could say 5 halves or 2.5, because if you plug in 2.5 times 2, you get 5 minus 5 is 0. And where's my other vertical asymptote?
Negative 2. 0. Oh, yes.
0, right? Because if you plug 0 in for the first factor, you get 0 times 2 times 0 is 0, minus 5 is negative 5, and 0 times negative 5 is 0.
5 over 2?
5 over 2?
Yeah.
Just set the bottom factor equal to 0.
Okay.
Set 2x minus 5 equal to 0, and like Luke did, and solve it, and you'll get 2.5 for x. Okay, so those are my asymptotes. In fact, the way Luke said it, 2.5, it's helpful to have a decimal when you've got a graph. Okay, it's a little easier to figure out where it is. All right, there's 2.5. And what was the other one? 0? Okay. So if you look at it, this graph can't cross the y-axis because the axis is an asymptote. All right, so we'll see what happens when we try to find where it crosses the y-axis. Something's going to happen. All right, horizontal asymptote. Let's start with the EVM. Okay, for that, I like to go back to the original because it's all multiplied out. Jack, what's the highest degree term in the top?
3x the second.
Yeah, and in the bottom?
The 2x the second.
And if you reduce that, what do you get for your end behavior asymptote?
3 over 2.
Yep, 3 over 2. And now let x get really, really big in that fraction I just put a box around. And that'll tell me my horizontal asymptote. Okay, what happens as you let x get really, really big? What does that fraction approach? Yeah, Adrian? Nope, it doesn't approach infinity. It just stays the same. Okay, there is no x, so it just stays the same. And it's a horizontal, so what letter should I put? Y. Okay, so y equals 3/2. What is that as a decimal? About 1.5. This graph is going to look very similar to the last one. Okay, it's going to be in those three pieces. X-intercept. Okay, let y equal 0 for that one. I'm going to hold off on finding the x-intercept because that would be, I mean, I could do it. I just have to solve this equation. Just set the top equal to 0. 3x squared plus x minus 4. Unless that factors, it might factor nicely. Let's just try quickly. If I have to use quadratic formula, I'm not going to solve it. So I've got 3x and x, two numbers that multiply to give me 4. I could try a 1 and a 4. And let's try, we're going to need a plus and a minus. So let's try plus and minus. Does that work?
Wouldn't it be 2 and 2? Does it have to be 1?
So that gives me 3x squared. That gives me minus 3x plus 4. Negative 3 plus 4 is positive 1, and 4 times negative 1 is negative 4. So that's how the top factors. So I can find my x-intercepts quickly. It's x equals, what's the second one? That one's quicker. 1. And x equals negative 4/3. Okay, how did I do that? I just set 3x minus 4 equal to 0. And it's negative 4/3. So this one's going to cross the x-axis twice. All right, let's see how that's going to work. It's going to cross here. So it's going to cross in the middle section. And then it's going to cross in the left section. That's about negative 1.3. Okay, and your y-intercept. Okay, we already said we don't have a y-intercept, so let's see what happens if we try to find it. What's 0 squared?
0.
Times 3?
0.
Plus 0?
0.
Minus 4. So the top is negative 4. And what's 0 squared?
0.
Times 2?
0.
And what's 5 times 0? What's 0 minus 0?
0.
0. Can I divide by 0? No. So there is no y-intercept. The graph never crosses that axis. Right, so the last thing I'm going to do is just check a couple points on my table. You could type in either the original or the factored one. I'm going to go with the original just because if you make a mistake when you factor it, that could cause some problems. All right, so as I'm typing it in, you should be thinking about values near the asymptotes that we can check. Okay, or if you have your calculator, start checking them yourself. Okay, what's a value? Let's look at my asymptotes. Just to the left of 2.5. 2.499, and we're at negative 3,000 something. Okay, so just to the left of 2.5, we are way down here. What's a value just after 2.5? Well, Fred,
2.5.
it's a value just after 2.5.
2.5. 2.1.
That's before.
2.6.
Even closer than that.
2.59.
2.51.
Yeah, so if you're at 2.5, something just after it is like 2.51 or 2.501. Okay? So just after 2.5, you're at positive infinity. Okay, what's a value just before 0? Just a little bit to the left of 0. Negative.
0.01.
Yeah, like negative 0.01 or 0.001. Okay, just before 0, you're going to be way down here. And what's the value just after 0?
0.01.
Sure, 0.01. And we're way up at positive infinity. Okay, I know as I head to the right, I'm going to have to curve down and never cross that asymptote. So there's that section. Here, I'm going to come up. I'm going to cross right there. Keep heading that way. And now in the middle, I've got 3 points to connect. Okay, I've got one up at the top, one in the middle, one at the bottom. Connect it, but just try to make it curved. Okay, the best you can. Okay, this graph doesn't have as sharp of a curve in the middle. It's this one's a much smoother looking curve in the middle. Okay. And also notice it looks like the graph stops. Okay, it shouldn't. It really should keep going up forever and down forever. Yeah, but that's basically what we drew.
Why does it stop there?
Just because as it starts to get too steep, the calculator has trouble with it. Anything that's really, really vertical, the calculator can't draw. And it gets very, very steep. But that's why you have me. Because I can draw.
Yeah, that's why I said, here's whatever this is, Hager.
All right. So for tonight, not every problem is graphing, because some of them take a little bit of time, but some of them are. So if you want graph paper, just let me know, and I can photocopy some. Right, but on 234, I want you to try 1 to 5 odd. Okay. 9 through 11. 15. 17 to 22, 23 to 25, 29, and 33. And those are all, just do all odds. Except 17 to 22, but everything else is just odds.